from my team will share some very early research projects on these topics. So the concept of world model is an AI model that is able to predict and simulate the future state of digital or physical world. So it is a very promising method for further strengthens the general ability of an AI model. However, the path towards the world model is not very clear currently. So that's why we organize this event today. We are going to share our very early results, and we also want to foster collaboration, embark some discussion on these topics. So we are very happy to have estimate researchers as speakers today for this event, such as Professor Liu Ziwei and Professor Mike Shou, to share their profound thoughts on these topics. Additionally, our event is also featuring the talented PhD students. They will enrich our discussion with their very fresh perspectives. I also would like to extend my heartfelt thanks to our organizing team, including Ma Le from our open source team, and Abigail and Xueru for their efforts for the organization. This is making this today event possible. And the special thanks is also going to Liu Anna for facilitating online translation services. So I encourage everyone can immerse yourself for the following up presentations and actively engage the discussions. Together, let's explore the frontier for the world model and the transformative AI technologies. Okay, so our first presentation will be started by Professor Liu Ziwei for introducing his research on 3D generation and modeling. So let me briefly introduce Professor Liu. Liu Ziwei is a Nanyang assistant professor at NTU with MM Lab. Previously, he was a research fellow with CUHK and UC Berkeley. His research interests include computer vision, machine learning, and computer graphics. Ziwei received his PhD from CUHK, advised by Professor Tang Xiaou and Wang Xiaogang. Ziwei is also the recipient of MIT Technology Review Innovators Under 35, ICBS Frontiers of Science Award, CVPR Best Award candidate, and the WAIC Yunfan Award. His work has been transferred to products including Microsoft Piece, ScienceGo, and Google Clips. So let's welcome Professor Liu to give our first talk.
Okay, so thanks, Josh, for the nice introduction. So it's also my great honor here. So since I think it's quite a small lineup, so let's keep it a very engaged discussions. If you have any questions or you want to discuss, you can interrupt me and we can have some in-depth discussions on the topics, right? So actually the topics I want to discuss today is on this multimodal generative AI with foundation models. So multimodal means we want to engage as much as the different visual signals, like the 2D, 3D images and videos. And for the foundation model, that is, we want to build models that can leverage the large language models and large multimodal models, right? I think here is a kind of prediction by a very famous consultant company that is by 2027, the creators won't have to be technical. They just have to be creative thanks to all these potential automation tools. But after you've seen all these amazing works like by ByteDance, so we can safely changing the prediction to 2024, right? So this year we already have very powerful automation tools that you can use. Even you don't have the expertise of AI, you can use them to create. So here I think I show the landscape of this AIGC this whole AI generated content for the movies, for the games, for the VTubers, for the animation. If you see the whole pipeline from the scripts, you can use it in large language models to the layouts, to the 3D. We have the 3D gen models that is very good at generating like object and scenes. Then we have these visual effects. You can use the video gen models, and finally we have some this kind of VFX. So we also have some work on that. So essentially for the whole pipeline, we can use nowadays these AI models to replace part of it. Of course, in the long run, we hope to build end-to-end models with controllable signals. But now we try to break down into several parts. So our visual world, I think, from my view, it consists of three very important visual aspects. The first is called avatars. Our humans are very familiar with humans, right? So we want to interact, so we want to create humans. So that's why avatar is so important and has a very huge markets. So since our humans have a rigid, like these body structures, you have 2 arms, 2 legs. So it's also, I think, one of the most matured technology nowadays. Then we can move to the objects. So objects compared to the humans or the avatars is definitely more complex because it's quite diverse. So in the visual world, we have like more than 1,000 categories or 2,000 categories out there. So how can we build models to also generate these objects? And finally, the scenes. So this part, I think, is the most appealing, but it's also the most complicated ones. You want to deal with the very large scale unbounded scenes, both indoor and outdoor, both natural scene and urban scene, right? So I will introduce our works on the 3 different realms. So due to the time limit, I will not go to the kind of the technical details. So if you're interested, check out the project page. We have open sourced most of the works. So first is on the avatars. So I think avatars, our exploration are from 2D to 3D to 4D. So on the 2D side, you already know nowadays we have stable diffusion, right? 1.5, 1.6, XL, something like that. Even though we have these very powerful models like stable diffusion, it's even quite hard to generate perfect humans. So sometimes you notice it's kind of lose some fingers, right? Or the pose is unnatural. So that is because the current stable diffusion don't have the structural information. So the key insight of this work is to kind of design a new type of diffusion models that have this explicit modeling of the human structures, like the depths, like the pose, like the surface normals. With all this structural information built into the models, you can have a very coherent modeling of the human images. So I will give you some of the examples here. So these are all generated by our models. You can see, you can use the pose as guidance, generate these 2 humans. You can also try to explicit model the depths out there. And it even have very complex interactions, right? So you know that for AIGC, it's very hard to generate composition or interaction between humans. However, after you build in this structural guidance, it's become easier, right? So that's our key takeaway message. And here is the results. So all these images, they are generated by the AI models. You can see the prompt here. And the kind of the high-res 1K resolution images here. Man sitting at bus, looking away from the windows, right? Even with this teddy bear. So we'll show that it's have better quality than stable diffusion, and it's more stable, right? And the second one is that we want to go to from like 2D to 3D. So at the time, I think it's the NeurIPS 2023 papers. So there's very few works that can like build diffusion models on 3D humans, right? If you want to build 3D models on like diffusion models on 3D humans, you have to find in the right representation. So what is the representation for 3D humans? So here we propose this called prim diffusion. That is, we represent human bodies using these primitives. You can see, given one image, we can translate it into some volumetric primitives. So each primitive you can think of is a small part that represents local regions of humans. So in that way, we can train a diffusion on this part from the noise to this structural representation. So it has very nice property. That is, you can do editing, you can do feed-forward inference, right? So it's not an optimization-based method. It's a feed-forward-based method. So it's very quick. And you can see here is the results of the denoising process from the noise to the primitives. It has a very nice structures of the kind of the mesh and also have the textures out there. You can also doing this novel pose, right? So since it's primitives, it is deformable, and you can use your favorite motion sequence on these avatars. So after that work, we still trying to improve the quality, right? We feel that, okay, there's a quality gap for the humans mainly lies on the textures. So because the structure of the human, you can always represent using like simple models plus some deformation fields. But for texture, it's very hard. So how about we explicitly use some UV map, like here, to represent the textures. So that's called struct LDM. It's structured latent diffusion for humans. So now you can generate this whole bunch of 3D humans out there with 3D consistency, different clothings, different layouts, different poses out there. There's also another feed-forward model. So good thing is that you can also do in this editing. Of course, I will show next in this work. That is it's called Fashion Engine. So after building these foundation models for 3D humans, so like the layman users, they don't want to just doing these unconditional generations, right? They want to give one reference image, just do editing, like try on, like to changing the sleeves, right? Something like that. So we show that we can like leverage this disentangled representation of the UV map of the textures and structures to do all the editings out there. So maybe I will close the sound here. Given one image, right? You can doing this sketch-based editing, make the sleeve longer, and you can choose your favorite pose. Different pose, you can choose the view of the person. You can choose the shape, slimmer or fatter, right? Something like that. And finally, you can do in the animation. So this is the online real-time demo, right? So our models can run real-time on actually on GPU, right? You can do much better if you are doing some engineering work to make it run on CPUs. Yeah. So after that, we are also trying to build in this animatable 3D text to humans. So you know that nowadays people use these Gaussians. That is actually the work last year. So using Gaussians to replace NERF because it's faster and achieves comparable performance. So here we show that you can do it also on humans. And I think it's very valuable for the assets creations for games, right? So sometimes when building the games, it's very time consuming, very expensive to design different characters. So using this work, you give some text prompt, you can change in the kind of the clothing of the colors. You can also change in the different settings, right, out there to generate this avatar. So this is also pretty quick. Just in seconds, you can get this very high quality 3D layouts out there. You can also do animations out there. That is the 3D text to humans. And finally, we want to focusing on the motion generations, because after we getting a very good 3D humans, so the motion, what we have shown is all predefined, is retrieved from motion gallery. So if you want to generate a very fine-grained novel pose, novel motions, how can we do that, right? So we propose this fine motion. That is, we can use the large language models to break down your prompt into actually the prompt for different parts and also across time, so that we can generate very fine-grained motions out there. So here is the one of the examples that we can leverage the language model, the foundation models, to describe how your left and right upper limb will move. Of course, we have some transformers. It's actually MOE structures, mixture of experts. So each expert is a part of human body. So here is the results. You can kind of try to describe the head movements, your limb movements, and out there. Right? So due to time limit, I will stop just here and go into the second part, that is objects. So that's that. So avatar for the research on this side is very near the market, right? Because it's pretty mature and we have very ready to use models for humans. But for objects, I think it's still in this rising phase. That is, we need good enough data sets, good enough models to generate diverse objects out there. So our first work is still an ongoing efforts. That is, we're trying to build in a very large scale 3D object data sets. So it's called OmniObject 3D. So it's 1.0 published last year. And this year we have this 2.0 that we will have like double the numbers of the categories and also adding more modalities, adding more annotations out there. So I think it's now the largest real-world scan objects. So many of you know another is called Objectverse. So that is kind of from the web. Many of them are CAD models. So all the objects here, they are real scan objects. So using these data sets, we are also adding these text annotations into different aspects. So you have the summaries, it's a teacup, you have the appearance, it's a relatively small teacup with a brownish red exterior and white interior. So we give these very fine-grained prompts and also the text annotations. Material, is hard, reflective, smooth surface, style, and function, right? So using all these annotations, maybe you can leverage all the prompts to train a very good text-to-3D models, right? You can specify the function, specify the style, specify the material and appearance to generate the truly good 3D models out there. And we have our first attempt. It's called DiffTF. It's a 3D diffusion transformer, right? So you know that Sora model, they are diffusion transformer on videos. And this model, I think it's one of the first models that tries to build in diffusion transformer for 3D objects. So we're just using one model, we can try to generate over 200 different categories out there. So after that one, we're thinking of how about we try to also capture real-world objects instead of generating from scratch, right? Without generating from scratch. So that is another work is called WorkSurf that can do this very fast 3D objects reconstructions. Comparing to this previous news, so it takes hours to optimize. Our model only needs like minutes. You can get a very good scanning of your favorite objects. So for example, if you have your own teddy bear, right? So you can just using your mobile phone to take a sparse view of the images, and after that, you can reconstruct within minutes, get all the mesh, texture, and import to the digital world to play with it, right? So that is our work on this very fast 3D capture. And finally, I think I will talk about the scenes, right? So scenes are most important, I think, but it's the most kind of complicated ones. So for the scenes, our first attempt to solve that is to try to do this text-to-3D environment. It's called text light. So it's not truly 3D because using one text prompt, like this brown wooden dog on lake surrounded by green trees during daytime, we only can generate this 4K resolution with HDR, this high dynamic range, this image. So this image is a pseudo 3D because you can't work inside, right? You can just view the 3Ds. You can see the results. I think it's pretty good. We can cover in this indoor, outdoor. So all the VR environments, 3D environment are generated by the models. Just given this prompt, you can generate the bedroom, you can generate a car park, right? And also like other kitchens of the buildings. And we also have demos out there. You can describe like this brown wooden floor with white wall. Then you can generate indoor interior. Of course, you can do in the renderings and put novel things inside. For example, this one. So this one is a very classic objects in the graphics domain. You can see the reflectance, the lighting, they are pretty realistic. And of course, you can put a robot head inside. And finally, we can take a VR view of the whole room. So after that, we are thinking about building a true 3D generative models for the scenes. So that's the scene dreamer. It's called unbounded 3D scene generation. However, for the scene generation, there's one big problem. That is, we don't have enough data, right? So for the humans, you have a bunch of data, either indoor or in the wild. For the objects, there are some efforts to building a large-scale data sets. However, for the scenes, it's very hard to capture, right? You can't take your 3D capture equipment to outdoor and to try to capture all the mountains and the lakes out there. So our idea is to leverage the abundance in the wild to the image collections. So we advocate that we should learn 3D from 2D, right? Instead of learning from the 3D itself only, right? So it may be a hybrid approach using both 2D and 3D supervision is the best. So using these collections, we can generate unbounded scenes with multi-view consistence, with these well-defined geometries, and also different scenes and styles, right? So it's have the explicit mesh, so you can build that into your game engines. So with all these 2D image collections, 3D models out there, you can generate infinite 3D world as you work around, right? You can have your own island, your own lake out there. So it's just like a game engines. Just learn from 2D image collections. With different styles, winter, summer, or with different camera trajectories, it's either like the drone view or a street view, something like that. So however, this work is only focusing on the natural scenes. A lot of people is interested in this urban, like 3D cities. So if we can generate 3D cities, we can also help with urban planning and also a lot of very interesting stuff. So can we also do the same on the cities? So the answer is yes. We can kind of leverage the Google Maps, right? We can kind of use the Google Maps with different layouts, with also the street view images to train City Dreamer, right? That general models can generate unbounded 3D cities. So here's a real-time demo. You can load a layout, your favorite layout. Of course, you can edit on that. You can choose the angles. You can first have your geometries out there, and then you have your textures. And if we import that into the UE, that is Unreal Engine, you can have a very nice 3D cities generated by us. So it's a City Dreamer. We can have very good geometries out there. And now we want to put humans and cars inside so that you have very realistic city simulations. And another ongoing work is called Gaussian City, because that work is pretty slow. The City Dreamer, even though the quality is very good, it can't render in real time. So here we also want to build in Gaussians inside, so it can boost to 10 FPS. So it's a near real-time renderings of the 3D cities. Of course, we also have another work on the indoor. So due to time limit, I will just show the results. You can work inside, like using this text to 3D. You can work into your kitchens to see the 3D views out there, bathroom, a Chinese kitchen, or other things out there, right? Here's your bedroom or living room with a TV, right? You actually get the virtual tours of any of the rooms you want. And of course, we also want to doing this very fast capture. So if you remember, we just introduced a work on this 3D object capture. So here we have another work on this scene capture. So if you go to hikings into some park, use your mobile phone, take several images out there, we can generate this virtual 3D reconstruct virtual 3D scenes also within minutes. So after all the avatars, object and scenes, finally I will briefly talk about our future work or our visions to how to unify them to build truly foundation models, right? So one of our recent efforts called large motion models. So many of these avatars, objects, or scenes, they involve some movements so that you can bring in images to video or bring in 3D to 4D. However, a lot of the works, the academic groups are tackling, they are separated. So some people are working on music to dance. Some of them are working on text to motion. Some of them are working on the code speech gesture. So they are separate tasks. So we are asking one question. So can we using one unified model to tackle all the tasks that involve the motion prediction? So the answer is yes. So we show that using just one model, we can outperform all the previous social models by the specialist models out there. So due to time limits, I will not go into the details. So in summary, we collect very large scale data sets, try to unify all the annotations, train a large transformers, and get the results, right? Of course, we have another work that is not just generation. It's called 3D motion captures. Just giving one monocular videos on web, like this one. We can extract all the motions and apply to either avatars or 2D reference images, as you like, to generate a very good dancing moves, right? For videos or for other like different media. So of course, we find that in the AIGC, in the generative domain, the scaling law still holds. As you add more data, more training instance, you can dramatically like lower this prediction errors out there. Also, larger model, larger data always leads to the better performance. So here we, of course, also started how you can mix real data and synthetic data, right? As you know, the real data is not always enough and balanced to train good models. So we also leverage the synthetic data. We finding a very good mix between real and synthetic can lead to the optimal training of the model. So here we also try to build another demos. You can replace this Captain America into a robot. Or you can create your own La La Land out there. You can extract motions, replace to another avatar of this La La Land scenes. And finally, I think it's called Digital Life Project. I will not show the demos here. So the major idea is we want to combining all the technologies we've introduced. That is how to generate motions, how to generate avatars, how to plan in the movements, how to understand the interaction between humans, right? So we want to truly build a digital brain, digital bodies, as well as the interactions between them. And so that we can truly build in some like digital life, right? So you can have some of their own personalities. You can also know some social intelligence, know when to shake hands, when to hug, right? Something like that. So I will show a very short clip showing the capacities out there. So all the dialogues, the speech, the sound, and the motions, they are synthesized. So we have predefined personalities out there. This one is AI researcher, and this one is another AI characters created by this one. Yeah.
Hello, Jishu. I'm Xiaotao, an autonomous 3D character with social intelligence.
So he knows that when this first meeting, you should like wave your hand. Then when they are getting more closer, they're starting to speak with each other, have these discussions.
Enables evolving relationships, while MoMat Mogen technology allows me to express these connections through lifelike 3D motions.
Then their relationships still involves, right? So the motion is listens attentively, and his is speaks with excitement, right? So you have another large language models behind to guide their movements. So now they become lovers, so they hugs and also hold the arms out there. Yeah. Right, so we can have some AI write the scripts, and we can also translate scripts into some these whole actions, emotions.
I'd love to watch it with you. Jishu.
Okay, so finally it's the goodbye, and I think that's also the end of my talk. And thank you. Yeah.
Thanks for the excellent talk and the very cool demos. So any questions from the audience regarding Prof. Liu's talk?
Hi, Professor. I'm a PhD from NUS, and I want to ask what's the inside of your motion network, the final part. What's the inside that you can outperform all of the specialist models? What's the key insights? Thank you.
Okay, I think the key insight comes from two parts. The first part is how to unify the data from different domains. So as you know, like in academia, different people propose different data sets. They have different formats, different distributions. So you have to finding a very good guideline that is how to combine them with a desired distribution. So that is the first key. The second key is that how to handling the conflicts between different like the body part movements. So for example, in the cold speech gesture, they're focusing on these upper bodies. They have a lot of like descriptions and motions on this one. And then in this dancing, music to dance, they have these lower body things. So your architecture should be able to disentangle these two and using part of data to learn like only one part of the network so that you can leverage all the information out there. I think the key is from two, both from the data and the architecture design. Okay, so another question.
Prof. Liu, I have seen this triangle 1 year ago in your first talking. Now I have a new question about this triangle. Today we have many large reconstruction models for 3D, like we can, given a single view image, we can generate 3D object or 3D scene. But this triangle connects 3D scene and the 3D objects. But we still need many optimization-based methods to compose scene and objects. My question is: there any possibilities to train a large compositional model to compose scene and 3D scene and the 3D objects together without any further optimizations in the future in our community?
Okay, thank you. I think that's a very excellent question. So when I kind of showing the triangle here, I always want to link the different kind of vertices out there, right? So how to enable the interaction between avatar and objects, object and scenes, and avatar and scenes. So there are certain works I didn't show here. Our groups are trying to linking all these vertices together. So regarding your question, now there's a very kind of a large interest in creating this compositional generation, but most of them are optimization based. So I think one challenge for these large reconstruction models to generate this compositional content is that their data does not support. So if you see this Objectverse, so their compositional is very limited, right? If you train on the Objectverse or even on our Omni Object 3D, you can't get very good models. So that you have to leverage the 2D diffusion prior. But nowadays we have new opportunities. That is, we have a very good video models out there. If you just leverage 2D models, 2D model is not good at this depths, the configurations, the layout, the occlusion out there. If you have a very good video models, have these camera controls, have all this like the predefined this trajectories out there, you can get a very good guess of this kind of composition. So I think that's maybe one way to go. And I believe just within half a year, we can have a very good like large consumer models even for scenes. Yeah. Yeah. Okay. So another question.
Hi, Prof. Liu. I'm a PhD student from NUS. So my question is, do you believe a text-to-image, text-to-video model can be a world simulator, or do you think a 3D model is necessary for us to simulate the world?
Okay, thank you. I think that's a very kind of important question to answer. And everyone is actually in the room is wondering whether we can learn a truly world model from just 2D information, right? From my own opinion is that depending on the computation and the data, if you believe you have access to possibly unlimited videos out there to covering different physics, the different like corner cases and different lighting, different computations out there, maybe we can train a large transformers to kind of mimic or try to simulate all the kind of the world models inside. However, in the real world, we always don't have that much data, or your data set you have always some bias. It's kind of biased to certain content, certain motion, certain style. So in that case, we need some prior to guide our models to have a more stable synthesis of the visual world. So in that sense, I believe 3D is important.
Okay, we will later have a social session. So if you have more questions for Prof. Liu's talk, you can talk to him during the social session. So our next speaker will be Kang Bingyi. Bingyi is a research scientist at ByteDance. Previously, he was a research intern at FAIR, working with Xie Saining, and a visiting scholar at UC Berkeley with Professor Chaudhary. He got his PhD degree from NUS, and his primary research interests are computer vision, multimodals, and decision making. His goal is to develop agents that can acquire knowledge from the observations of data and interact with the physical world. So he is going to introduce a new foundation model for 3D perceptions, that is depth sensing. So let's welcome Dr. Bingyi.
Okay. So hello, everyone. My name is Bingyi. Today, I'm going to introduce depth anything, which is a series of models for molecular depth estimation. So I will first cover some recap of depth and depth estimation. Then since we have two versions of models released, so I will cover them one by one. So I'd like to start with some examples of how depth is used in real world. So the first example is 3D reconstruction from a single image. So with depth, you can view a photo from different perspectives. And the second example is converting 2D video into 3D video. So if you play this video with Vision Pro, it feels like you can interact with the objects in the video. And the third example is controlled generation. Given some reference images or videos, you can generate new images with different content, but with a similar structure. And the fourth one is about replacing LiDAR with RGB camera plus a depth model. And about this one, there's a little story. We know that Tesla is using FSD, a pure vision system, right? So this is because Elon Musk believes that humans can just drive without shooting LiDAR. And so do cars. So about 3 years ago, Elon Musk made a claim on Twitter saying that as vision processing gets better, it just leaves radar far behind. And back to that time, a guy challenged him with an example like this, shown by this photo, I think. So there are two tunnels. One is real, and another one is a painting on the wall. So he just asked, how would vision handle this? And fortunately, our model is quite robust to this example. And this is why some people in the community believe that our model is somewhat evidence for Elon Musk's claim. So, okay, now let's talk about the molecular depth estimation. So previously, to have depth information, there are three typical ways. The first one is about stereo matching, which means you have two cameras, and they are taking photos at the same time, and you extract features for the photos, and do point matching and calculating the disparity, and then you have depth. A similar but more complicated procedure applies to structure for motion. But for depth sensors, it's a little bit different. So if you have a camera that can shoot lights, when a light collides with some objects, the light will bounce back and be received by the camera. So with the time difference between light emission and reception, you are able to calculate the distance of the object. So in this way, you have depth. So however, in our real world, RGB images are very cheap to obtain because we have smartphones. But the depths are not, because either the equipment is expensive or the computation is expensive. So this motivates us to study molecular depth estimation, which just predict depth information from single RGB images. So we have to mention one pioneer work called MADAS. So I think it's probably the first one to propose the concept of zero-shot molecular depth estimation. So previously, we have a scenario. We want to have a depth model for this scenario. We have some training data and we have some testing data. We train on the training data and testing on the test data. But all the data are from the same distribution. But MetaS is different. It tries to train a model on a mixture of data sets. So here's the data sets used in MetaS. So we can see these data sets are from different sources. For example, the first one is from depth sensor, second one from structure for motion, and the others are from stereo matching. So however, training a model with such a joint data set is not trivial. This is because the depth value differs a lot from data sets to data sets. For example, in an indoor scenario, the depth values might be just a few meters. But in an outdoor setting, it might be thousands or hundreds of meters. So this will pose severe optimization issue. So to address this problem, MetaS proposed relative depths. As shown here, the D is a depth map or disparity map used in MetaS. And the TD is the median value of the depth map. And SD is the standard deviation of the depth map. And then we can have D hat, which is a normalized target. And a similar thing applies to the prediction D star. We can have a normalized D star. So then the loss function is applied to the normalized target and the normalized prediction. And the rho here is just the L1 or L2 distance function. And let's see how it performs. So I've shown by the figures here. So you can see animals, people, and cars, bus. I think it's pretty well, right? So this is also our first impression on MetaS when we started this project. So we have to ask one question. So if MetaS is so good, is there anything else we can do? So we run a lot of testing on MetaS, and we found that it actually doesn't perform very well in the wild scenarios. For example, some randomly token photos or pictures. Yeah. So there's another question. So is there any models that are able to provide very strong in the wild generalization ability? And the answer is yes. This reminds us some foundation models in language and vision. For example, ChatGPT, Clip, and SAM. So all the only common thing behind all these models is about data scaling and model scaling. Therefore, we decided to do data scaling for depth estimation. So first, we just put all the labeled data together. And in total, there are 6 data sets and around 1.5 million of images. So although these are all the data we can have for depth estimation, but it's still very limited, especially compared to the data used for other foundation models, for example, SAM. So we turn our attention to unlabeled images, which are very cheap to obtain, and they are very diverse. So we built a data set with some academic data. In total, there are 62 million of unlabeled images. So the next question is how to effectively leverage this data to train a depth model. So we first train a teacher network solely on the labeled images. And then we use this teacher model to do pseudo labeling for all the unlabeled images. Below are examples for the pseudo labels generated by our teacher model. You can see it looks pretty well. So, however, naively putting all the labeled images and the pseudo labels together doesn't work very well. So we'd like to highlight 2 key practices to make it work. The first one is we add strong data augmentation to the unlabeled images, but for the labeled images, it's just some weak augmentations. And the second one is we introduce a knowledge distillation loss function to distill knowledge from a pre-trained vision encoder DynoV2. And this one is very important. Before we came up with this idea, we actually conducted a pilot study. We just add another auxiliary loss. The loss function is about thematic segmentation. We try to help depth estimation with thematic segmentation because the semantic masks are also some low-level features of the images. Unfortunately, it doesn't work very well. So we finally came up with this DynaV2 feature distillation loss function. And as shown here, the cost means the cosine similarity between the student features and the teacher features. And we have a tolerance margin. It means that when their similarity is larger than some threshold, the loss will be just discarded. Okay, so I think I'll just skip all these numbers. I think they are talking about the same thing. So our model is the best. Yeah. So let's see some visualization. So with the help of unlabeled images, we can see that our models is strong than methods in just robustness. For the quality, I don't think it improved a lot. Yeah. And here are some video examples. So I think the superiority of our model become more evident in the video scenario. And this is a control net results. I think with our depth model, you can take a look at the flowers, the facing direction is kept in the generation. And this is video editing. So we have been talking about the advantages of our model, but is there any limitations? And the answer is yes. So the prediction is just lack of details. Here is an example. We can take a closer look at the box of the wheel. You can see it's almost totally ignored a bad model, right? So, but is it really possible to get this? And the answer is again, yes. So there is a concurrent work called Marigold. So by feeding the same photo into their model, it gives us this prediction. You can see this box is very clear, right? The details is very good. So by putting Marigold and the depth anything we want side by side, we found that Marigold is very strong at producing fine details, at producing robust prediction for transparent objects and reflective surfaces. But they are often distracted by the textures of the image, as shown by this example here. So the textures are very complicated. So the results generated by Marigold is more like an generated image instead of a depth estimation result. So what is the model we want for depth estimation? I think it's one that can achieve the best of these two words. So we have a comparison between Marigold and depth anything we want. There are two main differences. The first one is they are using diffusion model. We all know that this one is the generative model. And another one is that they are using pure synthetic data, while we are using real data. So a lot of people believe that the details of Marigold actually come from the generative model, because we know diffusion is able to generate very high fidelity images. But we instead pay more attention to the data part. Let's see what's wrong with the real data. So here are some examples of the real data. For example, the first one is from depth sensor. You can see this is the ground truth labels. It has certain noise because, for example, like transparent objects, we know that the light can easily pass through glass, right? So that's why it makes mistakes in these regions. And for stereo matching, we know that when the object is too far away, stereo matching doesn't work very well. And similar for structure from motion. If we train a depth model with this kind of data, the prediction will just make similar mistakes as the training data. You can see here, and also the person. So another limitation of real data is lack of details. For these two examples here, even though there is no mistake, but they are just two calls. So we turn our attention into synthetic data. Let's see how, okay. So it has two advantages. The first one is visual details. You can see for this image. So in the boundaries and the thin objects and the small objects, it's I think the labels is just perfect, right? And for transparent objects and the reflective surfaces, since we have the 3D model, we can also have real ground truth for this kind of data. So if we train a model with the synthetic data and apply it to this new image and compare it with a model trained with real data, it feels like a short-sighted person suddenly has its glasses on, right? Okay, so if synthetic data are so good, why they are not popular before? To answer this question, we trained a series of models with different pre-trained vision encoders. They are BEAT, SAM, Sinclair, and DanoV2. As shown by the figures here, I don't think basically none of them work very well. There's only one exception, which is the largest one, is the DanoV2 Giant. So what does this mean? So it means that we conclude that utilizing synthetic data is non-trivial as there exists distributional shift from synthetic setting to real world setting. And also synthetic data doesn't have a very big coverage of the diverse things in real world. So how to effectively use synthetic data from depth estimation? We'd like to highlight two key points. The first one is use DanoV2 Giant, not even smaller ones. And another one is use large-scale unlabeled data. Let me show you why. So this is a model trained solely on the synthetic data. You can see it will make a clear mistakes in the clean sky for clouds, right? And this is another example. A person sitting in front of a screen. And we can see the prediction by the model. The head and the body is just a disjoint, right? So by adding unlabeled images, all these issues are gone. So actually, for this situation, this is our intention because we know that in simulation, all the skies are just very clear. So in real world, you have clouds. So this is our intention. But for the second one, it's just an emergent behavior of the model. Because in synthetic data, you don't have any people, you don't have any bodies. So it will make mistakes for persons. So now we are ready to have the final framework for our depth sensing V2. So we first train a teacher network on purely synthetic images. And then we use this teacher network to do pseudo labeling for all the unlabeled images. And then we only use the pseudo labeled real images to train student networks. Okay, so here's a comparison of V1 and V2 and Marigold. So you can see compared to Marigold, it's faster and lighter because Marigold is using diffusion. And compared to V1, it's more fine-grained and more robust to, for example, transparent objects. So as shown by this figure here, you can see the background is very clean in our model, but the Marigold is just noisy. And for this person, similar thing happens. The head is gone, right? Yeah, but here is the head is kept. So this is a demo video, I think. It's very robust to weathers, even though your photos are paintings or something. Okay. Okay, so here is some numerical comparison between depth anything V1 and V2. So is there any interesting findings? I think the awkward thing is, although we observed a huge improvement visually, but numerically, there is almost no improvement, right? Yeah, so why is that? This is because in the evaluation datasets, there is also full of label noise. So similar, here is just a few examples. The noise is very similar to the one I showed for the training data. And and this is our prediction. And for example, this one. So we are able to make a clear, correct prediction for this pillar, but in the ground truth labels, they are gone. So as a result, so better models might have lower scores for the current evaluation benchmark. So we developed another evaluation benchmark, which is a sparsely labeled evaluation dataset. It means for each of the image, we will randomly pick 2 points, or one is closer to the camera, another one is farther, and we will do some manual labels for this kind of sparsely paired points. And this test has the following advantages. We have preset depth at relationship because they are all manually labeled by ourselves. And they have very diverse scene coverage. And the third advantage is that they are all very high resolution images, because in the previous evaluation benchmarks, they are just some low resolution images like 200 by 300. Yeah. So and it covers a lot of scenarios, including outdoor scenarios, indoor scenarios, object underwater, and transparent. So by doing classification of this kind of data set, we compare some community models and our models. We can see Marigold can only achieve 86 points of accuracy on this benchmark, where our model, even the smaller, even the smallest one, is larger than 95. Okay, so here are just some ablations to show the importance of the labeled data, unlabeled data, sorry. Okay, now let me introduce the core team members of this project. So this project was initially proposed by myself, and the data scaling roadmap was set by myself. But most of the work are done by our intern Li He. Has done a great job during this project, and he is what introduced the unlabeled data. And Zilong consistently provides insightful discussions throughout the project, and he's right there. And Jiashi, so without his support, this project won't be possible at all. So we also have some external collaborators, and Xiaogang, Zhao Zhen, and Heng Shuang. So that's it for today. Thank you very much.
Any questions?
I'm a PhD student from NUS. Thanks for your talk. I have a question. Depth anything does well on relative depth estimation. How about the metric depth estimation?
So we have tried to fine-tune our model for metric depth estimation. Since for metric depth estimation, you can only have a limited number of data. For example, in the indoor scenario, you can only train it with indoor data, and so the results looks good, but the generalization ability is kind of poor.
Follow-up question. So do you have any insight how to improve the generalization of metric depth estimation?
So that's a really good question. I think a lot of people in 3D are thinking about the metric depth estimation. So I think probably directly estimate the metric depth from an image is kind of an U-post question, right? So I'm thinking about solving this problem in another way, which means if you have some reference. For example, with our iPhone, we know there is I think almost every iPhone comes with an low resolution like it's just maybe 100 by 200 resolution. But with this kind of reference information and plus a strong relative depth estimation model, probably we are able to tackle this problem.
Any other questions?
Hi. Sorry, I didn't get the point of depth anything V2. You said you train the teacher network only on synthetic data and use it to label real-world images. How can it overcome the sim-to-real gap? How can we use such a teacher network to label all of the data? Thank you.
So let's go back. Okay, so so the first important thing is about Dynamo Giant. So take a look at this example. So this is a model or a series of models trained purely on the synthetic data and test the model with real-world images like this one. So we can see the Dynamo Giant is already produced very robust results for this one, right? But all the other pre-trained vision encoders cannot. So the first key is that we must have a very strongly pre-trained vision encoder. Yeah. So the second part is for this case, because sky, we can easily detect the skies with a semantic segmentation model. Then after you detect the skies, you can manually correct the labels. Yeah. So with this kind of filtering strategy, we are able to fix this problem. But for this one, it's just an emergent behavior. I don't know why. Yeah.
Okay. So if there is no other questions, let's thank Dr. Bing Yi for the nice talk. And our next speaker is Dr. Jian Feng. Okay, Jian Feng joined ByteDance in the last year, and as a research scientist, he got his PhD degree from NUS. He once did an internship at Meta Reality Lab, and his main research interests are 3D understanding and creation, including 3D avatar and 3D object generation and modeling. He once received the Best Paper nomination at the CVPR 2021. Okay, let's welcome Dr. Jian Feng for introducing his recent work.
Okay. Hello, everyone. Thanks just for introductions. My name is Zhang Jianfeng, and I'm a research scientist in ByteDance. And I'm mainly working on 3D content generations from multimodal inputs, like the 3D generations from text, images, or even videos. And today I will introduce my work, Magic Boost. My recent work, boost the 3D generations with the multi-view condition diffusion models. This is today's outline. I will first introduce some background knowledges, and then I will dig deep into our methods and experimental results. And lastly, we will have a Q&A sections. So first, let's discuss why we need the 3D generation techniques. 3D generation techniques has a wide range of applications, such as in games or movie visual effects and AR and VRs. With an effective 3D generation techniques, people can easily customize their own characters, their own assets or visual effects. And with this, they can use them to interact with the other users in the games or 3D content platforms. And the 3D generation techniques can also serve more fundamental applications. For example, it can be used in smart cities for urban planning, and it can assist the designers for industrial design, and it can generate high quality molecular structures to help the researchers for better studies. So recent 3D generation techniques can be divided into 4 categories over time. In the neural radiance field arrows, people combines the differentiable renderings as well as the adversary supervisions for 3D content generations. Representative works such as EG3D, StyleNerve, and Guess3D. And such kind of methods do not rely on any 3D data or multi-view images. And they can, these methods shows the good novel view synthesis results. However, they usually generate low quality mesh, and such methods are limited to, they typically limited to objects of specific categories. So, with the recent developments of the diffusion-based text-to-image generation models, Google has introduced a skill distillation sampling-based methods. They use this SD as guidance to optimize 3D representations for 3D generations. Representative works are dream fusions. And such methods also do not rely on any 3D data or multi-view images. And they leverage the 2D priors of the image generation models. And thus they can generalize to more diverse objects and geometries. However, such methods is very slow. It typically requires an hours to optimize an object. And these methods are sensitive to the hyperparameters and prone to the genus problems. That means the generated objects may have inconsistent views. So to improve the generation efficiencies, recently researchers have proposed two-stage pipelines. That is the multi-view generation and then reconstruction pipeline. Representative works are Instance 3D, Wonder 3D, and LGM. In this pipeline, with the user inputs, it will first generate some multi-view images based on these inputs, and then it will reconstruct the corresponding 3D objects given these multi-view inputs. And such pipelines achieves a much faster inference speed compared with the optimization-based approach. And it better alleviates genus problems since it uses the multi-view priors. However, since the generated multi-views are not always consistent, the inconsistency of the multi-view images will affect the reconstruction qualities. It will produce the inconsistent geometries and even blurry textures. And also, such pipelines generate geometries and textures jointly. And that means this kind of information are entangled in the generation process, which makes the generation more challenges. So most recently, researchers have proposed the native 3D generation pipeline. Different from previous works that leverage the two-stage pipeline, it directly runs the latent space in the high-quality 3D data. And they use the diffusion models to denoise the latent space for 3D shape generations. And such methods can ensure the generated geometries are relatively sharp and clean. And with the generated geometries, we can further do texturing or materials modeling based on the generated texture, based on the generated geometries. And such methods clearly disentangle the geometry information with the materials or textures, so it makes the generation process more controllable. And in today's talk, I will mainly focus on the two-stage pipeline, the multi-view generation and then reconstruction pipelines. However, our method can also be applied to the native 3D generation methods for the further texturing or refinements. And this figure shows how the multi-view generation and reconstruction pipeline works. First, given the user's input, the input can be like text, images, or even both. And it will first use a multi-view diffusion models to generate the pseudo multi-view images. And then it uses a fast reconstruction models to reconstruct the corresponding 3D objects from these multi-view images. And this process is typically fast. It typically rely on, this process can typically be finished within like 10 seconds. However, when we take a closer look at the results, we can see that the generated results are very coarse. We can see a clear performance gap between the generated multi-view images with the original inputs. And the third column shows the rendered RGB and normal maps. And we can see that the geometries of the reconstruction models are not very sharp. So we hypothesize there are two main problems limit the reconstruction qualities. First of all, current reconstruction models usually leverage the triplane representations as well as the neural radiance field representations. So the limited resolution of the triplane and the heavy volume renderings of the neural radiance fields make the model hard to generate high quality objects. And you can, as you can see in these figures, you can see the generated armors is overly smooth in both textures and geometries. And the second reason is that since the generated multi-views from the first stage is not always consistent, so this inconsistency will lead to the blurry results. For example, in these figures, the eye regions of two views differs, and this results in the final generations. The eye regions of the final generations is blurry and may even have the inconsistent textures or incorrect textures. So in this work, to address these problems, we propose MagiBoost, a multi-view condition diffusion models that to leverage the multi-view images to optimize to refine the cost generation results. And our motivation is that even though the multi-view images may not be very consistent, they still contains the rich information and about the details of an object. And by leveraging such informations, the model can learn to generate high quality null views, and such information can provide a more precise guidance for the SDS optimizations, and thus can achieve high quality texture and geometry refinements. So what does MagiBoost actually improves? First of all, we can see that in the left is the cost results. We can see it's blurry, but however, after a quick refinement with MagiBoost, the geometry and textures become sharper. And this is the second example. The eye regions from the cost results are not consistent. However, after refinement, our method can provide more consistent supervisions and helps the models to generate more consistent and sharper results in the eye regions. And here is the model architectures of our approach. Our approach is a multi-view condition diffusion models that build up on the stable diffusion architectures. It takes the multi-views and the corresponding camera parameters as the inputs. The multi-view images are generated by any two-stage method. And it aims to synthesize a null view X given the corresponding target camera pose, CX. And this process can be formulated in the equations in the bottom of the slides. So by leveraging the multi-view informations from the first stage, the model can learn how to generate a more consistent null views. And with such information, we can leverage it to optimize the geometry and textures of the cost results. And in order to synthesize null views, it's very crucial to capture both the high global features with the high-level signals, as well as the local features with the details. So in order to encode the global features, following previous works, we leverage the clip encoders, frozen clip encoders, to encode the images for global feature extractions. And since clip models encode images into a highly compressed feature space, so we found that only use the first input view is enough to generate a good result. So after extracting the global features, we inject it into the diffusion models through the cross-attention modules, following previous work like IP adapters or image rings. And for the local features, for the local features from the multi-view images, we propose to extract the lower level features from through the denoising UNet at a fixed time steps. That means we extract this information from a clean image from the clean multi-view images without adding any noise. So we will consistently set the time step to 0. And these multi-view local features will be injected into the diffusion models through the self-attention modules to encode the 3D correspondence informations. And we also propose control labels in this model. These control labels enable the users to adjust the conditioning strengths of different views. For example, if we know that a specific view generated from the first stage are not ideal, we can manually adjust it to a lower score to allow to reduce its effects on the no view synthesis, and vice versa. And for the target views, we will always set the control labels to 0. And since our model is trained on the observers with the ground truth multi-view images rendered from the 3D objects, directly applied our model in the real applications will produce the suboptimal results. This is mainly due to the domain gap problems because in inference we cannot ensure our multi-view images has the same qualities of the images used during training. So we apply some data augmentations to our training data. And this slide shows some concepts of our augmentations. First, we will add some noise to the ground truth images to simulate the inconsistent conditions in the inference. And secondly, we will randomly blur some images to improve the model's robustness. And thirdly, we will randomly drop some views to make the model more robust to missing data, and also facilitate models to learn enough information from other available views. And our control labels during training is also determined based on the scale of the data augmentations. For example, if we are using a larger augmentation scales, we will set a small control labels to reduce its influence on the no view synthesis, and vice versa. And after training the Magic Boost model, we can use the multi-view images generated by the multi-view diffusions as inputs. And then our model can provide the SDS guidance to further refine the cost reconstruction results from the two-stage methods like instant 3D and instant mesh. And specifically, we will first convert the generated mesh into 3D differentiable representations. And this process is complete by using a fast nerve, that is instant NGP. And this process is very fast. It usually takes about 1 minute to finish. And after initializations, we can refine this converted nerve using the SDS supervisions with a small range of denoising steps provided by the Magic Boost models. And since our model leverage the multi-view informations from the first stage, it can provide a more precise SDS guidance to quickly refine the cost results and improve its both textures and geometries in the final generations. And this process is very fast. It usually takes about 5 minutes to complete all the process. And since we know that the SDS-based optimization usually introduce oversaturation problems, so in here, we introduce an anchor iterative update loss to alleviate such situations. Specifically, our method is inspired by the NERF editing works. In the NERF editing works, usually you will first randomly render some images, and then they will edit these images iteratively, and then use the update images to supervise the NERF optimizations to get the edit NERF. And in our pipelines, we use the similar strategies. So these figures illustrate our concepts. So we will by taking the multi-view images as inputs, we will first use our Magic Boost to generate some random views as the anchor images, and then we will add a small noise to these anchor views. And after that, we will use the same models to denoise these images to get new ones, but that is more consistent with other views. And after that, we will use these images to supervise our NERF's optimizations through an image MSE loss. And such a simple techniques can help the methods become more robust to inconsistent multi-views generated in the first stage. And we build our methods on two state-of-the-art two-stage pipelines, that is Instant 3D and Instant Mesh. And our method is also compatible, also adaptable to other two-stage pipelines that can provide multi-view informations as well as the cost reconstruction results. And this slide shows the results of our method based on Instant 3D. We can see that the generated results from the Instant 3D in the second columns is cost. It contains some floating noise in the generated geometries, as can be seen in the normal maps renderings. And you can see in the second example, the donkey's eyes contains some inconsistent textures, and the textures is blurry. This is because the generated multi-view images from the first stage is not consistent. However, after a quick refinement of our approach, you can see both the textures and geometries become much sharper, and the inconsistencies and blurry textures in the second examples has been corrected. And this is the results of our approach on Instant Mesh. The Instant Mesh results are also not very sharp. And you can even see that in the first image, the turtle's appearance, the legs of the turtles is broken. However, after our optimizations, quick refinements, we can get much sharper results. And the turtle's legs broken has been corrected. And you can even see that in the third example, an elephant made of oranges. You can clearly see that after our refinements, the detailed textures of the orange segments can be clearly generated. Yeah, you can see it in the normal maps renderings. And here we visualize the optimization process of our approach on Instant 3D and Instant Mesh. And this result proves that our method is robust to a different approach. By taking the multi-view images as inputs, our method can bring a quite significant improvement on the generation results. And here we provide some qualitative comparisons. We merely compare three SDS-based methods on the image to 3D tasks. Here we compare our method with 0123 XL, Magic 123, and ImageRings. And we can see that all these methods generate suboptimal results. The result from 0123 XL contains the floating errors on its geometries. And the Magic 123 tends to generate dark textures on the back views. And the generated results from ImageRings are not well aligned with the input images you can see in the first examples. However, our method built up on the Instant 3D achieves a better result. It has sharper textures, correct geometries, and better alignment with the input images. And we also compared with some other results, boosting results based on the two-stage method Instant 3D. We compare Stable Diffusion and 0123 XL here. We didn't compare ImageRing here because ImageRing has its own canonical camera space and not suitable for refinement. And you can see both the refinement result from Stable Diffusion and 0123 is not aligned with the initial cost objects generations, and it cannot provide a sharp textures and geometry refinement. However, our method compared with them can achieve a quick refinement and can better preserve the identities from the cost results and can further improve the details in a short time. And here is some qualitative comparisons. There are three metrics we use here, and we can it basically evaluates the generation quality, the render images qualities, and the alignment of the text input and image input. And we can see that our methods achieve the best results on all these three metrics, which also demonstrate the effectiveness of our approach. And finally, we conduct simple ablation studies. Here, we first evaluate the data augmentations proposed in our approach. We can see that if the model trained without the proposed data augmentations, the optimized the 3D objects may contain some blurry or geometry errors. For example, in the red box, you can see the hippo's mouth and eyes are not consistent, and the geometry is not correct. However, the model trained with the data augmentation strategies can achieve a better result. And finally, we ablate our anchor iterative update loss. A more common approach is to just apply the L1 or MSE loss on the multi-view input images. However, since the multi-view images are not always consistent, so if we simply apply the L1 loss, it will produce the inconsistent textures in the regions that are different between views. However, our method compared with the L1 loss can achieve a better consistent textures, and that is more realistic. And here is more texture mesh result generated by our Magic Boost. And if you are interested in our work, you can scan the QR code for more details. Okay, that's the end of my talk. Thank you for your listening.
So, any questions from the audience? Okay, I think that's already the time for the social session, and we are providing the dinner and the snacks over there. So if you have any questions, you can chat to Dr. Jianfeng directly. So it's time for the dinner and the social.
B-star. 4 minutes. Please take a seat.
the second half of today's event. And the first speaker is Professor Michael Shou from NUS. Professor Shou joined ECE department at NUS as a tenure track assistant professor with the NRF fellowship in 2021. Before joining NUS, he was a research scientist at Facebook AI. Professor Michael research focuses on computer vision and deep learning with an emphasis on developing intelligent system for video understanding and creation. Michael was awarded Wei Family Private Foundation Fellowship from 2014 to 2017. He also received a Best Student Paper nomination at CVPR 17. His team won the first place in the International Challenge on Activity Recognition in 2017. So let's welcome Professor Mac for introducing his recent work on video and other.
All right, yeah. Thank you, Josh, so much for introducing me and having me here. It's really my pleasure here to be today. Let me see. Okay, yeah. So my research mainly focuses on video, and with half of them are on understanding, another half would be generation. This kind of like two pillars nowadays in any topics in computer vision. So for understanding, it's mainly like Gemini, whatever you give it Gemini a video, and then you can ask a question, and they will give you answer. And for generation, essentially it's the reverse problem. Given the textual description, we can generate the video content. So there have been a lot of definitely very promising, exciting products from like OpenAI, ByteDance, but definitely there are still a lot of challenges down the road. That's why we are here, right? And for understanding, I think there are two challenges we have been recently trying to attempt to address. One is about how can we deal with more complicated video tasks. Another one would be how to deal with limited in-context length, because always this we are using large models nowadays, but the GPU memory is never enough. And for the first one, we have been using kind of like the idea of convert video signal into texture tokens. But for the other one, actually, we are trying the opposite direction, which is to convert text into visual signals. So let's get started with the first one. For many of these tasks, for example, Gemini, they are very good at simple tasks. For example, what is the color of the stock? But this is simple factoid-based tasks, and we are more interested in some more, like complicated tasks. For example, we have been exploring this so-called AI assistant scenario, which means that ideally, if I don't know how to use this laundry machine, microwave, then there could be AI assistant on my cell phone that guide me through the process step by step. For example, I could ask question like how to start this cotton wash, and then the AI assistant will tell me the answer is first to turn here to garden, and here actually could be grounded to specific region on user's cell phone or smart glasses. And then the second step would be press here. And we have been working on this for a few years, but then we realized it's always very hard to collect data and validate the results. Because we require real human beings in the process, and the students, we definitely don't want to collect those data. So we want to do coding, training models rather than collecting data. So there are also people exploring this idea of video summarization, and this kind of ALM as AI agent works pretty well in this space. Essentially, given for example, half-hour long video, we want to condense it into like say 1 minute long video with some texture summaries alone. But there is a problem. It's very subjective to evaluate. For example, I could have my version. You could have your opinion about what the summary looks like. So therefore, we finally end up with this task so-called GUI, graphical user interface, on the screen. So essentially, when we look at the computer screen, over time, it's streaming video input. And then we can have some kind of AI agent that takes control of your keyboard and the mouse to perform the action for you to automate some operations on the software. So that in the sense of it can improve your productivity to help you use this complicated software. So here's a quick demo. So since there are also people from overseas, I guess online, DBS is a primary banks in Singapore, essentially. I believe all of you know, in the room. So I always have this problem of how to get my last month statement, like whether for visa application or whatever, I need the bank statement. So because we need to first click on like my account and then click another button somewhere else. But how can I just maybe get this easier? So we developed this AI assistant. Essentially, later on, let me try to play this video. You can ask just a simple question, assist me in assessing my September statement. Then it will take control of your mouse and keyboard and then click like my account. And then next step would be click view e-statement. And then it will click on like view PDF. So you get it by just one single sentence. And also it can work with like this software, like Office, Word, like convert into 2 columns. And also about kind of how to set up your Zoom meetings with some passport. And also some more complicated software, for example, this one, Adobe After Effects, which essentially people use in post-production of video creation. And it involves a lot of functions and definitely requires a long time to learn how to use this software. And then now you can, with a single task, ask me to place the text behind the boy, and it will automatically control these like functions, keywords, to complete this. So this is a final demo of our work, and this work is called Assisted UI. So essentially, it's a multi-agent collaboration framework. It has 4 agents. One is the planner, which is to decompose a complicated task into several subtasks. And the other 3 agents are actor, critic, and GI parser, which are essentially to execute the action. And for the planner, the idea is that let's think about how human achieve this. Essentially, when I don't know how to use, for example, Adobe, this kind of software, so I look on YouTube and found some tutorial videos and then learn from that by watching the video. So similarly here, we could find an instructional video detailing all the functions contained, demonstrating how to use that software. And then using this instruction video as input along with the query user's question, essentially, for example, apply push transition on the second slide of the PowerPoint. And then given these 2 inputs for the planner, it will generate some outputs, essentially the planned steps. And it's essentially just a simple LLM model. And the output could have multiple hierarchy. For example, at the high level is text 1, select the second slide, and task 2 is to choose the push transition effect. But for this second task, you can actually also decompose it into like subtasks as well. So once we have these step-by-step plans, then now the problem is like how we can actually achieve that, to execute that. So we have the 3 agents, parser, which is essentially to detect the to understand the current screenshot information, to get where is this buttons, what is the meaning of this button, where is this panel. And then when it will output the actions, generate some outputs for the actors to digest, and the actor will generate the action to be executed. For example, click these like coordinates. And then once it has been clicked, the screenshot will be changed basically, and then you can compare whether it achieves your ideal results or not. So I will go into this in detail. So for the GUI parser, essentially the input will be the screenshot, and also we have some software metadata as well. And then we run different computer vision modules like panel, layout, segmentation, icon detection, OCR, vision models. And then you will be able to get a output, essentially a sentence. For example, like the panel name, title bar, essentially you can, is this like title, oh, sorry. So this title bar would be essentially corresponding to this yellow rectangle here. And then you have its coordinates as text tokens in the output of the LLM. And for each panel, you have its elements like paste is corresponding to the first icon, and also its coordinates, and so on and so forth. We convert this visual image essentially into a sequence of tokens, sequence of text. So that's about parser, and the next agent is this actor. Essentially, is a LLM model, and the input are purely text, and then we have this kind of very complicated prompt input. So the first instruction actually is use py auto GUI. So py auto GUI is a library, contains a lot of function for you to control your computer, and then it can be executed by calling these functions. So the instruction would be like use py auto GUI to control the computer's mouse and keyboard to complete the given task. And then the second component of our prompt is the current task. So it's defining basically what we want to do. And finally, we have this task screenshot in text format as input. So then the input, and finally you have the output is simply this like code format output. Click this coordinate, and then we can execute using the py auto GUI. And once it has been performed, once the action has been performed, the computer state will be changed. So you have a new screenshot. And we fit this two screenshot before and after for comparison, and also as long as we have other kind of instructions into another LLM, like for example, the instruction would be like assess if the user's actions achieve the intended result by comparing the GUI before and after the action, and then we have the goal definition, we have the action, and also the pass the screenshot before and after, and the output would be would essentially defined as like successful and finish and what's the reason. For example, in this case, the output will be success true and finish true, and the reason is this transition menu appears. So it indicates the execution is successful. So when we get started with this task, actually there is no like available data set or benchmark. So the one of the effort actually is to create the data set and benchmark. So the process is simple that we look out on the YouTube, these tutorials about how to use software and ask human annotators to find out this, identify the videos contains a lot of information. And then for each video, we can define the task, define essentially what to do for each task, and then ask the human annotators to perform the actions to actually achieve that task. But we don't need to record the whole process. We only need the final state file. We only store the final execution result for comparison. I mean, to compare whether the algorithm AES execution result, whether it's successful or not. Because you only need to compare whether the results is ideal or not. You don't really actually care about what we kind of like work path we conduct. And we have about 100 tasks collected over 9 software like PowerPoint, Excel, Word, calculator. And recently we have, I think we have an upgrade version as well to make it even larger. And this is simply application to show that our model, this kind of multi-agent framework is better than chain of thought, React. And hopefully, the idea is that later on in the future, I don't need to prepare this PowerPoint by myself. It can be automatically generated. Actually, I previously I always had to have different presentations. I have my own these PowerPoints, and Josh told me I need to use this ByteDance format stuff, and I have to ask one of my students to help me to do this reformatting. So I guess this is also another use case that CGI can help us to automate this kind of productivity demands. So all right, so the SysGI essentially is to convert visual into textual information, text tokens. So we have been recently thinking about, can we do the other way around to convert text into images? And why we need to do that is because we always talk about like in context length is fixed, is a limited number of tokens. So how can we do like long context? And for multimodal ML training, the Flamingo or whatever models, they have been essentially switched from just using simple image text pairs to use lengthy interleaved documents like a website or a book or whatever. It's a very informative input data. For example, this is an interleaved doc. You have this dog image and then the company text like this is a very cute dog, and then another image and some text. So given this interleaved data, what we will do is fit these texture tokens into our LLM model. So this part is our LLM model. And then for the images, they are not go into this LLM model, but instead they go through another visual stream. So for each image, we go to a visual encoder, and then this output embedding or whatever features they are fused into the LLM through the cross attention. But the problem with this document or interleaved data is it often contains a lot of text tokens, a lot of tokens. For example, this Open Flamingo 9B model are actually not able to utilize all the text tokens. It subsamples only 256 tokens from the whole document for each sample. But in contrast, we wanted to actually, make full use of all this information. And for the image, when we look at it, no matter how dense information content in one single image, because we do the resizing or whatever, actually each image only we require 14 by 14 tokens to represent one single image. So this motivates us to think about, can we actually convert unlimited kind of text tokens into an image which has a fixed number of tokens? So that's why we try out this off-the-shelf tool, which is essentially to render text as image. So essentially, there's some very good existing tools that can do that to render this kind of like text on this paper, and then for the background you can choose some kind of like whatever background you like. And then for each image, we only need fixed 14 by 14 tokens to present it, so it's quite memory friendly. And also another advantage would be, for LM now, we are talking about 9B, 7B, whatever, even 50B models are quite expensive. But for vision model, it's relatively small. Like vision to transform a large model is only about like 300 parameters, million parameters. So when we actually put this fit this text tokens through the visual stream, is much more efficient, because it only goes through a small network compared to LLM. So with this kind of motivation, we come up with our framework, and in its framework, it's very essentially similar to this Flamingo architecture. For the gray part, it's essentially the Flamingo. You have the visual text is interleaved data, and for text goes through the LLM model, and for visual, we go through the visual stream. But what is different is that we have capability to process additional text tokens, and for these text tokens, we render them as one single image or multiple single images to go through the same visual encoder. And then it will be goes and later on to extract features and then fit into the LM kind of like cross attention. And we use the we add additional loss, is a contrastive loss for text-centric, because essentially we want to do some kind of regularization between this visual string and the text string, which makes them kind of like more aligned in the feature space. So essentially, during training, we actually fit through these like text token features and also the visual features to let them kind of like contrast to each other, so as similar as possible. And finally, you could see that this is the result, and on the left-hand side is the GPU memory consumption. So this curve in the bottom is the original Flamingo model. And when we use like 256 tokens, it's okay. But when you further increase it, it will exceed the memory we can afford. And this memory, I mean like 80 GB memory. But once we add on to the visual in context approach, it's simple, but we can accept actually 2,000 tokens. And for the flows on the right-hand side, like T flow, so it's basically smaller, better. And when our compute cost of using 2,000 tokens actually is very comparable to the original one of using 256 tokens. And here is just to show like the performance is better because we can digest more text tokens. How much time do I have? 10 more minutes. Okay, that's great. Yeah. Cool. Yeah. So so how I've been talking about understanding. So now let's talk about the other side, which is essentially generation. And I feel like the field is definitely progressing very fast. It has been just maybe 2 years, or definitely no more than 3 years, when everybody now kind of like work in this like video generation or whatever diffusion models. And about like in 2021 or 2022, these big companies, they like Meta, Google, they developed this video diffusion models which were very impressive at that time. And also at the university, we want to do this kind of research. But it's very hard because they do the very large scale training on like web video or whatever, even larger data set. It takes a lot of resources. But at university, we definitely don't have this kind of resources. So we have a crazy dream at that time. It's like, can we train a video diffusion model in 10 minutes, just use one single GPU? So that's why we come up with this idea of so-called turn video. Essentially, we have been thinking about what makes a video diffusion model, or what is different, video diffusion model different from image generation. We can already generate pretty good image content from stable diffusion models. And what maybe lacks for video generation is how we can inject the dynamics, the motion information. And do we need to learn the motion information from a lot of data? Maybe not, because like, for example, as humans, when we see a video, for example, on TikTok, and we can imagine another subject maybe is acting the same motion. We can have this kind of prediction or essentially do analog. So similar idea here. If I have wanted to generate, for example, a video of skin, then I can maybe provide the model with a skin video. So we have this skin video provided as long as this texture description. And then we only train our model, essentially training on our model on this like one single image video pair. And once it has done, then we can modify the texture descriptions, like for example, change it to Spider-Man or whatever. And for the approach, actually is straightforward because now we are doing 3D essentially video diffusion, so then we need to inflate the 2D model to be 3D. So then we do this kind of like add-on temporal attention, spatial temporal attention layers, and also this kind of like 1x3x3 the pseudo 3D convolution operations. And then one challenge actually happens in the spatial temporal attention because it's very computational expensive if we wanted to do attention across every 2 frames. So what we propose to do in this work is that we do this sparse causal. Essentially for each frame, we only let it to attend to 2 other frames, essentially the first frame and the frame right before the current frame. So the idea is when we look at the first frame, it will provide information of the identity to control the appearance. And for the previous frame, this kind of attention from current frame to previous frame is for maintain the consistency transition more smoothly over time. And it turns out it actually works pretty well. Like on the left one is the input video, the reference video. For example, our rabbit is sitting a watermelon on the table, and then by changing the texture description, we can do something like remove the watermelon or change the watermelon to a cheeseburger. And also, I think nowadays there are also even better approaches. So even without actually turning on any videos, they can do this kind of zero shot turning zero generation as well. But typically, when we do zero shot, the change of the object would not be that significant. If you want a very significant change of the appearance, maybe still want to turn on one video or even a little bit more, a couple of videos. So this is about how challenge of video generation, how we can save the computational cost. Another challenging, what we are very interested in is how we can generate longer video, because now we have been mainly generating a few seconds long video, but in order to generate 1 hour video or even just 1 minute long video is still considered quite a challenge nowadays. So this is actually joint work with Jiashi and my student Zhong Cong and some other team members here as well. It's called Magic Anime. We started with this, I guess the simplest task for long video generation, which is human-centric video generation. We have a lot of human data online. So the task is like give a reference image user provided. Then when I see an interesting videos, this dancing videos, then I can animate or make this like single image dance according to that another reference video, dancing video, and then that dance video could be actually quite long. So this problem has been definitely studied for a long time, but previously it's very hard to maintain the consistency of background, the identity, and often when the video is long, it's flicking. So we actually developed this framework Magic Anime, and then it turns out only requires 350 training videos that can do to train a pretty stable animation model. And this framework is of 3 components, 3 strings. So in the center is basically the diffusion model, and in the bottom part is the kind of like the control net. We extract the whole sequence from the reference video and then fit that as kind of a condition into the UNet. What is different is here we have a this like blue part, which is called appearance encoder. Essentially, it's a trainable copy of this UNet, and the purpose of this model is to extract the characteristic of the reference image. So the input will be the reference image and the output will be the condition into the union. And actually it turns out only this 300 or so videos already can help us to train a pretty good appearance decoder. And so once it has been trained, it can be used to digest, to process other people's identities, images. So that it's quite generalizable. And for video generation, especially long video generation side, we actually still do divide and conquer. Essentially, each long video sequence, we would divide into 16 frames, a sliding window of 50% overlap. So it's with 50% overlap, that means the second half of the sequence 0 would be actually the same as the first half of the sequence 1. By doing so, we can do something like interpolation, basically fusion, averaging in the when we do the denoising in the intermediate layers, so that can make the transition essentially more smooth. And also, we are initializing the model, the inference with the same noise, so it's like more consistent. So here are some comparisons with some old this kind of baselines. So the left-hand side is the reference image, and our method is on the right ones. And these are the other methods approaches. And also it can be used to animate other unseen domain images. And also recently we have been doing some kind of further optimization, like especially I guess what is more important is to scale as a training data and make it of like higher resolution and add more constraint, loss, optimization around the hand region and hand. So you can see the hand and face region, they are relatively better than the previous one. All right, yeah, that's all I want to share with you today. Thank you so much. And if any questions, I'd be happy to take.
Any questions from the audience? I have one question regarding the GUI agents. So how much of the training data you are using for the instruction tuning or for training the agent neural network?
Yeah, so because actually 4 different agents, and when actually for this GUI parser, which is more kind of vision centric part, we do require some of our own data, but it's not that intensive because we label this kind of data by ourselves. So it's only about hundreds kind of level. But during inference time, actually we do not, for give a new software or whatever, give a software, once we provide this instructional video, we do not need to actually train on this specific software. We only need the instructional video provided at the inference time as kind of like a part of the prompt. So it essentially does not require training for the model to be generalized to dealing with another new function or another new software.
Okay, thank you. Thanks for the excellent talk. So our next speaker will be Dr. Zhou Daquan. Daquan is currently a research scientist at ByteDance, and he is the recipient of the 2021 PhD dissertation award from Singapore Data Science. Previously, he was involved in the development of Singapore's first commercial artificial satellite. His paper coordinate attention for efficient mobile network design is currently ranked 5th on the CPR 2021 in terms of the number of citations and impactedness. And his current robust work, fully attention network, was adopted by the winning solution for the 5 segmentation checks in the 2022 visual robustness computation, and was integrated as a foundation model into the NVIDIA developer TO toolkit. His current interest is on video generation and video understanding. So let's welcome Dr. Da Quan for his presentation.
Thanks for the introduction. So my name is Da Quan, and I'm a team member of the team Magic Research, which is the organizer of today. So how did you guys feel the dinner today? Thanks. Yeah. So today I'm going to let me try this. I don't use this before. Okay, it's cool. So today I'm going to present our research works related to the line of video generation. So here is a brief overview. Say on the year of 2022, we released the first version of the latent video generation model. And this is also the first latent video generation model around the world. And then after that, we start optimization in different dimensions. For example, the algorithm or model efficiency, and then is the hardware efficiency. After that, we start optimizing the algorithm performance from two aspects. First is the spatial quality. Oh, it's here, thanks. And then after that, we start optimizing the motion quality. So the motion quality, when I put it here, I'm basically meaning is a long video generation, because only when the video is long, then you can see meaningful motions. So before we can do that, before we can do that, we have to create a long video data set. That's why we also do a video understanding model for the dense captioning, and it also achieved the state-of-art performance of 8 video benchmarks. So that's it. And today, all the previous works are basically ignored. So I'm only to present the last one, our latest performance video generation model. And you can see, in terms of the motion, is significantly better than all the previous works. Yeah. Let's just move fast. Later, I have a lot of examples to show you guys. Yeah. So when we talk about the video generation model, what do you guys think is the most important part? It's the GPUs, right? Everyone, I mean, it's like this. When we talk about a video generation model, we need to use a lot of GPUs. And here is a simple calculation. Say, on the left-hand side is the needs put for the video generation model, and then on the right-hand side is on average how many GPU cores was put for the video generation model, and what's the impact is quickly shown here. Say we have excellent works from Professor Maxwell for the tune of video, and we also have very good works, say for the way enhancer and animative from Professor Liu Ziwei, which is also sharing in the first part of the section. I mean, they are all very excellent researchers, and they put in a lot of efforts to improve efficiency, meaning use as less GPU cores as possible, right? And then they are doing very well on, say, improving the visual quality, the consistency. So the background is, you can see, is very consistent. But compared with those, I mean, the heavily trained video generation model, say from Sora, you can see the motion range is still relatively small. So that's one problem. And then the extend the scope, then the difference is even more obvious. So as you can see here, with Sora, of course, I mean, this is not a one-time work. They optimize it with very efforts, but you can see at least if we have a dynamic, I mean, in terms of motion, very good model, then when they put everything together, they can generate really, really fantastic video clips. So you can see here, only when the motion is very dynamic, it will attract your attention. Actually, I have sound impact, I have audio channel in this video, but it's not played here. Then it's also, I think, doesn't matter. Anyway, motion is today's focus, the main role. And this is also, you can see, when the motion is very large, it's really, really attractive. But it's not easy to use. I mean, besides the heavy GPU resource, if you want to achieve those results, you also need extensive training data. So here is a quick calculation of the number of video data used for the model training. As you can see, starting from the this one is basically for the ImageNet. It's not for the video training, but I put it here as a baseline. So now it's more than 100 million video pairs. Let's do a quick, simple calculation. Say when we do the training, each video we sample 65 frames, and for the size of 130 million of video data, then is basically more than 6,000 larger than the ImageNet. I think if you guys are with a PhD degree, then you must be familiar with ImageNet, right? So for many labs, they even cannot afford to train an ImageNet dataset. Now the size is say more than 6,000 larger than that one. Then how we are going to deal with it? Cannot. And even with those extensive training resource and the data set, the resulting model is not very good. For example, if we really want to use a video generation model to make a movie, right? We cannot generate a movie at one time. When we want to make a movie, what do? We will generate many movie clips and then put those clips together, right? So with this model, say if we have a scene which is a girl wearing a shirt and then standing in front of gate, and then the next one is wear a t-shirt, then you can see the independent generation will change everything. The idea is different. You don't want to your movie character keep changing at every scene, right? So even and this is actually very hard to achieve. Say even when I use very complicated promote to control the generated character to make it consistent, again you can see the character is actually changing very easily. Even though I specify it's a man, and then it has the night wearing, still cannot. So initially, when we want to solve those problems, first we try to use ID tokens to keep the consistency. For example, this one is Imagine Me. So what we do is with some given images, we will extract ID tokens, and then when we generate the videos, we will insert those ID tokens so that the generated identity is controlled. And then with this technique, even when we generate different movie clips, we can at least to ensure it's the same character. And then by putting all those movie clips together, we can somehow get a more movie-like scenes. But again, this is not satisfied, because if we want to extract ID tokens, we need some very faster training. Even though it's fast, lightweight, but we still need to train it. Then users will never upload some images and then use some GPUs to extract ID tokens. So here is our final goal for the video generative model. First, we want it to be lightweight, meaning we don't want to put in those much of GPU resource, and we don't want to use that much of data. But we want the generation process to be controllable, and we can generate, iteratively generate different video clips, and then we can put them together such that it is a movie at the end of the day. And then we don't want, when we use the ID to control the generation, we don't want it to be trained. We want to do it in a zero-shot manner. And when we extract the ID tokens, we want to use as less number of images for the ID token extraction as possible. Yeah. So combine everything together, we come up with this final solution. I mean, our latest research works. What we do is simply break down the text to video generation process into two steps. First, from the text to images, for those guys with video generation background, you have to note it's text to images, not text to image. It's different. And then the second step is image to videos. By doing this, we are achieving all the previous mentioned 4 advantages. I will mention 2 of them here. First, we are reducing the data demands. As the first step, text to image process only need the text image data, which is much cheaper and easier to get. And then for the second step, image to videos is also much easier to train compared with text to image directly. However, it is not easy. As I highlight just now here, we are using text or if we want to control the ID, we will use an additional ID image to generate a sequence of images, right? And then we have to ensure those images are having consistent IDs and attire or everything details, right? So when we are doing this research, there is no such method you can use. If we do independent image generation, they must be different, except OpenAI Diary 3, but they never tell us how they do it. So here is the first research problem we solve. When I say it's the first step, the text to images, I'm saying we can achieve the results such that different images are holding the same ID. This is also reducing the training difficulties or reducing the motion generation process significantly, because previously, say if we want to generate a very complex or complicated thing, right? We need to use a very complex or complicated text description. For example, for this very famous video generated by Sora, and this is the text prompt they use to generate it. I break down it into 6 parts. You can see it's very complex. So if you really want to train a model, you have to do at least 3 things. First, you must have a very, very powerful text encoder. And then when we say the text encoder is powerful, it must be large enough, so it's very hard. Secondly, you must train a very, very large or huge video generation model, because it needs to generate really, really complex video clips at one time. And third, you must have a very good or high quality video training data set, because during the training, you also expect the model to have this very detailed, complex text descriptions. So all those are very hard to acquire. But with our method, just now I show here, right? We don't need it because each image is generated with 1 sentence. For example, for this very complex things, I don't need to put all the text to generate videos at one time. I only need to input 1 sentence at one time, and then I generate 6 different images independently, separately, and then we combine all those images together to finally get a video. So this whole process is reducing the complexity or the learning difficulties of the whole model. How we do this? The key problem is how we can achieve a consistent IDs or attires details for all those images. So here is our method. Basically, we modified the attention or the image similarity calculation process such that previously for the self-attention, they only calculate the similarities within a single image. Now we expand the context into adjacent images. The key motivation is that if there are some components or tokens that are similar among different images, we want them to be the same. If they are different, then we want them to have no interfere or impact on the adjacent images, and leaving those parts fully decided by the text descriptions. So with this new self-attention calculation method, we come up with a new self-attention calculation layer. And then with this layer, we encapsulate into a self-attention block. And then with this block, we come up with a neural network design. This is fully modularized so that it actually supports scaling up if you have enough GPUs. And then with this new model, basically we can use different text descriptions to generate different images separately. And then at different styles, I'm sorry, I forgot to change the text here, but basically we also support the cartoon generation. Cartoon style generation. Uh, uh,
there are two methods then you can do as the adopt as the guidance signal for the driving behavior. One is the occupancy, that is predicting which area in the camera in the camera scene is occupied and the car cannot run into. And the other method is metric mono depth estimation. We do not predict occupancy, but we predict some depth information. Yeah, do you have any thoughts or rough idea regarding this comparison between the occupancy and the metric model depth? I guess the question is arise from the example, the Elon Musk comments.
Yeah. Yeah, I think, but Tesla is using FSD, right?
Yeah.
So actually, I'm not sure because I'm not an expert in autonomous driving. So for also for our model, it's some relative depth model. It's not a metric depth model. Directly estimating metric depth from a single image without any reference or supervision is kind of like a U-post problem. And I think if we have some low resolution LiDAR plus some high resolution relative depth model, I think probably to my view is the best way.
Okay. And also there are two more questions. The second one is whether the depth estimation model can generalize to wide angle images, such as the images captured with 180 degrees or even 360 degrees.
For relative depth, I think it can generalize pretty well. Yeah.
Yeah, but the that image is very tricky, right? Because the far away image, the end of the one side of the image is actually the same as the other side of the image. So even for this case.
Yeah. So directly apply this model to this kind of situation. Probably there is a generalization gap. But if you have some model data for this kind of situation, you try to train it or try to add this kind of data into our training data set. I think it will work well.
Okay. And the final question is, if we use a depth estimation result from any depth sensing model, can we use it to do the 3D reconstructions?
Actually, I have tried some examples. For example, in an indoor situation, you have, for example, multi-view images, and you can do structure for motion or directly have the camera pose. And if you try to align the relative depth with the structure for motion, sparse cloud points, and for simple structures, a simple fusion will give you a reconstruction of the room. But for a very complicated situation, for example, the room we are facing here is there are too many objects and too many small objects. So it's really hard to directly fuse them.
Okay, thank you. So the laptop is getting back, already get back.
So I'm back again. Sorry, guys. And let's continue. So just now I'm saying I'm showing how we can how we propose a new model such that when we generate images which is described by independent text sentences, then we can keep the details and the IDs. So here is basically a comparison with some other very intuitive or related baselines. First one is IP adapter, second one is model maker. So as shown here, basically our methods achieve the best trade-off between the text controllability and the image consistency. When I say this, the text controllability would be, say, if we are using an IP adapter, and then the IDs are kept very well. But because the ID controllability is too strong, then the text controllability is basically not that good. For example, for this one, right, the photographing, and then it's basically, it's not reflected. And then if we are using a photo maker, I mean, the ID is basically can be kept, but the attire or some details cannot be made. I think this is due to their training strategy, where they only focus on the IDs. So with this, we can generate very consistent characters. So the first application would be the comics generation. On the right-hand side is there is no ID controllability, and then we are simply generate different scenes with a text description, and then you can see the IDs are all consistent through the way. On the right-hand side is how we add in the ID image controllability. So when you generate the corresponding characters, then the ID are somehow related to the reference image you use. But this time, we do not need to extract the ID tokens separately. This is a zero-sum manner, meaning you can just upload your image, and then you can generate this kind of comics. And this is another example with Chinese text input. And then after we getting those bunch of consistent ID images, we can converting that into videos. So to achieve this, we train a separate video generation model where there will be two images as the conditions. And then the model basically will predict the intermediate frames between those two images. And then say if we have 3 images, then we will do the second, and we will use the second image and the third image as input, and then generate intermediate video frames. So by doing this, basically we can generate videos with infinite length. So here is the impact of video generation results with 2 images as conditions. Yeah, and then when we combine everything together, we can generate photorealistic video clips with infinite length. But of course, I can't put infinite length video here. So here are basically videos with time duration longer than 10 seconds. And this is with different styles, thick tone. You have a bear here. And here is some robotics and inside room context. So as you can see, the details for the car, and then for this room, we can see the wheel is moving forward, and everything is the motion in terms of the motion is larger than the previous method. So here is a quick demo of the work. So as you guys can see, right, how complete motions without only a partial of the motions compared with previous method. Excluding sorry. Okay, yeah. So that's it. Thank you.
Any questions from the audience?
I have a quick question about the GPU's resources of other companies. How do you get the numbers? I'm very curious.
Huh?
The GPU's resources for video generation project, how do you get the numbers of GPUs from other companies?
PM me separately. That's why it's also one of our team members. So I think because for some of the figures, right, they just put it in their paper. But for many others, we just check with them individually. That's why I don't want to talk about it now. Yeah.
Okay. Any other questions? Okay. Then thanks for that. Yeah. Our final talk is about learning some amazing image editing functions from watching videos. And the talk will be brought by Dr. Junhao, Liao Junhao. Junhao joined ByteDance as a research scientist since 2021. Prior to joining ByteDance, he was a research fellow and PhD student with NUS. He also did his internship at Adobe Research, advised by Scott Cohen, Brian Bryce, and Milo. His current research interest is lying on image and video editing. So let's welcome Junhao for the final talk.
So thank you for the introduction. So my name is Junhao, and today I'm going to present our recent work called InstaDrag, which is a drag-based editing method that we can learn from video data. So before we start, let me give a simple example to show you what drag-based editing looks like in practice. So assume that we have this beautiful photo of a cute cat right here. So let's say everything looks perfect except that I try to tilt it a bit to make the cat look a bit more closer to the camera. So what can I do with it? So maybe we can start by drawing a simple mask that actually delineate the area that we wish to edit, and then followed by giving a point pair, which is the red and blue dots over here, to show that maybe we will try to instruct the model to ask it to turn the cat's nose from the red dot to the blue dots. And then ideally, a drag-based method would give some results that look like this. So this is what drag-based editing essentially looks like. And then maybe we can continue doing by maybe dragging its leg over and then to obtain another result that looks like that. And then finally, we can also do some other changes like maybe making the flower a bit bigger by scaling it up by drawing a few points right here. And then we could give the final results over here. So from the previous examples, So from the previous examples, we can see that there are a few capabilities that drag-based editing can do. So probably the very first one will be doing some movement, like we can close up the crocodile's mouth. Or maybe we can do some shape deformation, like even we can bend the rainbow right here. Or maybe we can also deform the shape of the chair for maybe designing purposes. Or we can even do some things like changing the orientation, like we can turn the dolphin's head. Yeah, so right now, I would like to convince you like why do we actually need such a drag-based editing method. So existing image editing methods typically rely on some text prompts or masks for editing. So for example, like in Sharp Pix to Pix, it takes in like text instructions such as like changing style A to style B or replacing object A with object B. So unfortunately, using a function like this, it cannot do like very precise editing, such as if I want to turn the cat's head, like in the very first example, I can't precisely control where to move it to a specific location. And similarly for the in painting methods, such as stable diffusion, it takes in like stable diffusion in painting models. So it takes in like mask and then again a text prompt to do a editing. But unfortunately, because there's no specific instruction to tell it where to move or where to delineate like the structure or the shape of the final results. So there's no way to do like specific fine-grained editing like what we have shown earlier. So since I've convinced you like maybe why we need a drag-based method, so I'm sure, and after that we have seen like quite a few very amazing drag-based works coming out, and probably one of the more popular one will be DragGAN from SIGGRAPH 2023, where they show very good, amazing result at that time by having like a demo that can show they can make the lion opens its mouth or turn its head over, and then you can even lift the mountain. So that result was really impressive. But unfortunately, one problem with this DragGAN is that because it's based on the GAN method, which has limited capability for generation. So in other words, it might have some generalization issue. So taking this example, this statue image, if I want to turn this statue image over, so I need to rely on some GAN that are trained on statue images. But in reality, I might not have such a model. So the closest is I can maybe take a GAN that was trained on human images, and then what I get is something that looks like this, which is not plausible. So this subsequently motivates like a lot of different work that tries to employ such a drag-based methods on diffusion, the more powerful diffusion models. Like probably one of the more earlier representative along this direction will be drag diffusion, where they show relatively good generalization capabilities, such as they can drag like a synthetic image over here or paint oil painting and then other objects rather than those that are only available in the GAN domains. And then subsequently, there are so many amazing drag-based works coming out, like drag on diffusion, diff editor, SD drag, readout guidance, and more. But one problem with all this method is that because all of this essentially based on some kind of like latent optimization or gradient guidance, which means they are practically infeasible for real-time application because they are slow. So as you can see from the right figure, even the faster one, which is diff editor in this case, it also takes up to about like 10 seconds for one editing, which is extremely slow. And then next I will be showing you a demo on how it looks like in the drag diffusion. So taking an example right here, this is the live recorded demo that I recorded by myself. So I uploaded an image of a corgi here, and then I give a prompt, a photo of a dog, and then the first thing I do is to train a LoRa. The reason for this step is to make sure that the model actually memorizes the content of the image, so that when it drags, it will memorize the appearance and it won't shift the identity or appearance during the dragging process. Then during the training LoRa process, as you can see from the progress bar on the right, so it actually takes up about like 30 seconds to just this pre-processing step, and that's not even about like start dragging. So while waiting, and then finally, once after this is trained, we can finally start doing the dragging. So we can start by drawing a mask here to indicate this is the area that we wish to edit while keeping the other untouched. And then we can give some point instruction, which is a point pair, asking it to move its nose over. And then we can start running. Again, because this is a method that based on latent optimization, you need to wait again and for another maybe 30 or more seconds. So I will speed out a bit because that will take a lot of time. And then Oops, sorry. Yeah, about 30 seconds later, we will get results that look like this. So maybe it looks good, but unfortunately, if you want to do another round editing again, we have to redo the optimization process, which takes another 30 seconds, which in practice, I don't think is feasible. So hopefully until this point, I have convinced you that drag-based editing is actually important, and then it's also very essential to develop a fast and efficient drag-based editing for actual applications. So I would like to present you our work called InstaDrag, lightning fast and accurate drag-based image editing emerging from videos. So there are two main points from this title right here. So the first one is to being lightning fast. So as compared to a prior method, our method can achieve like 10 to 100 times speed out as compared to the previous methods. So which means it's ready for almost real-time interactions. And secondly, it's much more accurate than the previous methods. So in terms of both image fidelity or mean distance. I will talk more on this later in the later slides. So before we move on, I would like to give you a simple pipeline to illustrate what the process that looks like. And then I will delve more into the details. So starting with an input image, again, the corgi example that we have seen. First, we would like to give some drag instructions. So such as giving a mask or a point instruction to tell the model what we are doing. I mean, what we are trying to drag. And then this will pass to our InstaDrag model to obtain the results. And then if we are not satisfied with the result, we can continue passing this output image back to the input again and give another round of drag instruction and then do another round of editing and so on to complete a more complicated dragging process. So here are some of the goals that we wish to address in order to develop a fast and accurate drag-based methods. So the first is being fast. Secondly, we try to ensure there's no change in the unedited regions. And then thirdly, to preserve the identity when dragging. And then finally, to move from the source to the target locations. So the very first one is to be fast. So like what we have seen earlier, the problem of the previous method, why are they slow? It's because they rely on some kind of test time training or test time optimizations. So obviously, in order to become fast, we have to try our best to get rid of this process. So how to get rid? So one obvious way is to make it trainable by collecting data. But the main issue is that how to obtain such a data. So manually collecting such a data is not really feasible because we need to require, maybe we need to ask like a lot of like artists, professional artists to annotate a lot of such input-output pair for us, which is not only expensive and slow, but also making it very difficult to scale up. And maybe second approach will be rely on previous drag-based editing methods such as drag diffusion to help us to generate a lot of like synthetic training data to train our model. But the problem with this is that they might not be very accurate, which means the performance of our model, the upper bound of the performance of our model will be bounded by the accuracy of such models, which means that it will only make our model fast but not accurate. So we turn to see that maybe can we exploit some of the motion cues that naturally exist in the natural video data. So the idea is that the natural video data actually contains a lot of like very rich motion cues that encompass various transformations that are relevant to drag-based editing, such as like zooming in, zooming out, changes in poses, orientation, and so on. Like looking at the example below, we can see like, for example, the turning of the cat, or maybe the moving of the cow, or the scale change of the water drop. All these actually are pretty relevant to drag-based editing. So this makes us think maybe we can make use of this video data to form pair supervision to train our model. So that's for the first part where we solve the problem of being fast by using pair supervision from video data. Then we move on to the second goal, which is to ensure there's no change in unedited regions. So what does it mean by is that since we have a mask provided at first, we want to ensure that every pixels outside of the mask should remain unchanged throughout the editing, because we only wish to drag the region within that mask. So you might think this is precisely the editing of inpainting. So yes, actually we are relying our model based on an implanting backbone. So this is the architectural design of the backbone model. So we actually make use of stable diffusion 1.5 inpainting backbone, which takes in a mask image and a binary mask, and then a latent noise, because it's a diffusion model, that perform iterative denoising process until it obtain the final clean image. And then we move on to the third part, which is the identity preservation. So how to preserve the identity in order to make sure there's no change in appearance. So like in the example below, we can see that definitely the corgi on the rightmost is not the desired one because it's no longer the same corgi. And then similarly, if you apply to like human faces, we definitely don't want the drag person to look like another one. So how to do this? So of course, there are a lot of different ways, but in this method, we actually borrow the idea from Magic Anime, which Prof might explain earlier. So which is to make use of appearance encoder. So the idea is very similar to the reference only control, except that it takes in like clean image or latents as input, and then try to inject the appearance information to the network via self-attention operation. So as compared to clip image encoder, which can be only capable to maybe maintain some very rough color or texture. So appearance encoder is found to be more capable in terms of preserving fine-grained details. I will show you a very simple illustration on how to do this. So let's start with a self-attention operation, which I believe most of you are very familiar with. So given the input, then followed by a linear projection, we get three matrices, Q, K, and V, which represent query, key, and values. So self-attention operation essentially is computing matrix multiplication between Q and K transpose, followed by a softmax operation, and then followed by a multiplication with V. So essentially, it's trying to compute a similarity between each pixel in Q and then with all other pixels in K. And then we make use of this sort of attention operation characteristic to inject the appearance. So what we do is that we take in the reference image that we try to have a reference of the appearance, and then pass it to an appearance encoder, and then we obtain like a key for reference and then the value for reference as well. And then we simply concatenate K and K reference, V and V reference, and then do self-attention. By doing this way, so each pixel of query not only attends to all other pixels in key, it also attends to all other pixels in the reference key as well. So at this way, so you can actually borrow the appearance information from the reference image when doing the generation. So that's why the generated content will look alike as the reference image. So back to our architectural design. So right now, based on the previously seen impinging backbone, now we have the top part of it, which is an appearance encoder that takes in the reference image that pass to an appearance encoder, and then finally inject the appearance information via the self-attention operation into the backbone. So let's move on to the final part, which is the main goal of drag-based editing. So the question is how to move from the source to target locations. So until this point, like we have maybe like point pairs such as a handle points and target point right here. The question is how to encode point instructions. So in fact, we make use of the same self-attention operation to do this. So back to the same figure that we've seen earlier, which is the one on how we inject appearance information using appearance encoder. So in this formulation, what we can ensure is that maybe the generated content will look alike the reference image, like to ensure there's no identity change, but there's no constraint to ensure that what to generate at each location, which means we can't drag yet. So possibly with this formulation, we can only get results that look like this. A lot of different corgi that look very same. They are probably the same corgi, but they are all looking at very different directions. And this is not the one. We only want the one that actually follows the desired drag directions. So how to do this? Yeah, we actually make use of the same idea as well. So we take in the handle point and then the target point, and then pass it to a very lightweight point embedding network to get a handle embedding and target embedding. So the idea is very simple right here. If we want to do the drag, which means we try to make sure the query at the blue points, which is the target point, to look alike the reference image, which is the kref here, at the red dots, which is the source points. So what we can do is simply we just add the handle embedding and the target embedding to the corresponding Q and K respectively. So looking at this illustration, you can see that the Q is now actually can refer to the kref at the desired location, so that it can try to regenerate the nodes at the red point here at the blue point, which is essentially doing a dragging process. yeah, hopefully after doing this, after training the model, so the point embedding knows how to actually assign the weights. So the models learn how to actually make the two locations that we wish to move from A point to B point to be look as similar as possible to achieve the final dragging effects. So yeah, back to our architectural design. So this finally completes the puzzles by having the final component, which is point embedding networks that take in handle points and target points as the input, and then finally pass the point instructions into the network via the self-attention operation again, along with the appearance encoder. And then finally, we wish to get rid of text input. So why do we need to do so? The reason is that in dragging, unlike other text to image or text to video or other operations, in dragging, because most of the content are already decided in the input reference image. So regardless of how you drag the dog, you drag the dog's head on top, or you maybe drag his leg or do whatever, there's no change in terms of the semantics. So if you try to input another text prompt, so this might slightly incur more user burden during the interaction side. So we try to remove it by injecting the image semantic to the network by getting rid of the text prompt. So what we do is that we take IP adapter to extract the clip embedding and then finally pass it to the network via cross attention. In this way, we do not need any text input anymore, and all we need is just image, mask, and point pairs. Finally, to train this model, we freeze the backbone inpainting model as well as IP adapter and only train the newly introduced module, which is point embedding and appearance encoder in this case. So here I would like to present a few tricks that we found to be useful to improve the performance. So the very first one is having a noise prior. So as you all know, diffusion model actually starts from a randomly initialized Gaussian noise, XT, and then after several rounds of denoising, eventually reach a clean image. And a lot of recent work also found that manipulating the initial noise will have a direct impact of the final result as well. And then following similar, previous work, what we do here is that we simply replace the randomly initialized XT with a noise source latent, which means we directly add noise to the source image latent using the forward diffusion equations. So the result as shown at bottom here, so this actually has a rather strong performance on those examples that are with like not very rare kind of like color appearance such as neon lights. Yeah, but on general, it also helps in improving the overall appearance as well. The next one is to have a point following classifier free guidance. So as we all know, diffusion model usually employs some kind of like classifier free guidance, usually in terms of prompts, to ensure that it has a rather good prompt following capability. So similarly, in this case, since we are doing dragging, which means we try to make sure the point following capability is good enough. So what we do is that we have a point following classifier free guidance where we develop a CFG based on unconditional term that is without the points. And then as we can see from the bottom example, if you want to try to drag and lift up the mountain in this case, we can see that without CFG actually it's not working. And then with a constant CFG, it works, but there's this overexposure problem. So that's why we actually design the classifier free guidance skill, omega t, to be a time-dependent skill that decreases over time, which we found to be able to not only improve the point following, but at the same time also reduce the overexposure issue. Finally, I would like to show some drag engineering, I would call it like similar to prompt engineering in large language models to improve the performance. So the very first one is called point augmentations, where we found that like if we augment with more additional points of handle points and target points can better convey the user editing intention. So taking the top left example, if you try to drag the chair to make it a flatter one, so maybe with only 2 pairs of points, it's not enough, but simply adding 2 more points, we can successfully drag it to become to achieve what we want. And similarly for other examples, like the head case. And then secondly, another trick that we found to be useful is called sequential dragging, which is kind of similar to chain of thought in LLMs as well. So the idea is to break down the dragging into a sequence of shorter dragging trajectories. So assume we want to drag this high heel example here. it might be a bit challenging if you try to drag it all at once. But what we can do is to break it down into smaller steps, like drag it bit by bit, and then finally reaching the final results. So we also found that maybe breaking down this into a smaller problem like break and conquer, so actually it's much easier. Next, I would like to show some quantitative evaluation of our method on DragBench. We measure in terms of two metrics. One will be the image fidelity, which measure how good is the appearance, preservation, and second one will be the mean distance, which assesses if the handle points are successfully moved to the target points. So for the image fidelity, the higher the better, and then for the mean distance, the smaller the better. So as shown in this two table, our results is not only significantly faster as shown in table 2, where our methods can allow like editing within like 1 second for 512 times 512 resolution image, but at the same time, we do not sacrifice any accuracy. Yes, so we are also being more accurate than prior methods. Here, I would like to show some qualitative comparison of a method comparing with the previous works. So maybe one notable example will be the one from the last third one, which is the one dragging the camera down to reveal the girl's face. So probably this is the first one to be ever successful to do such kind of drag editing, where the previous one mostly failed on this. And then we also show more interesting results of our Insta-drag, like such as we can do like very interesting dragging, like dragging the giraffe to make its head shorter, or we can actually drag down the flower to reveal the face and do other kinds of funny stuff. And then finally, I would like to show some multi-round dragging as well. So like what I said in earlier, so in cases where you need like very complicated dragging, we need not drag it all at once. We can drag multiple times. So for example, taking the dog example, we can first drag its tongue, and then we can move its head over, and then we can drag its feet to subsequently reach the final goal. Yeah, so too long don't read. Sorry. Yeah, so we present InstaDrag, a high quality drag-based image editing, which allows editing in 1 second by learning from natural videos. So for more information, I will encourage you to scan the QR code to refer to our project page. And finally, I would also like to take this chance to thank my amazing co-authors, Eugene, Hansu, Vincent, and Jiashi. And then before I end, I would like to end with a short, with a demo video that I recorded in live demo to show that how does our demo actually looks like. So while playing the video, I can take more questions if you have any. But maybe let's get with the first video over here. So in our demo, we will take in like a mask to indicate the area to edit, and then followed by a point pair to indicate the direction to edit. And then you will notice that there are 4 results on right. This means that actually our result is really fast, that we can actually support like having multiple edits at the same time, and then allow the user to choose from. Because in a lot of cases, if you try to drag, there are multiple possible results. There are a lot of like diversity right here, and user can feel free to choose one that he or she prefers. So this is the benefits of being fast. Yeah. So thank you very much.
Any questions from audience?
So yeah, thanks for the great presentation. So you said that test takes quite less time with your method. How about
the expenses of training come from the testing time? But on the other hand, all our expenses come from the training. So once it's trained during testing, you do not need any like optimization anymore. You can just infer. But regarding the training expenses, it also depends on the GPU resources that we have. So in our case, we train on 8 GPUs, and then in order to reach a really good result, it might take 2 to 5 days. It depends on how good you want to reach. Yeah.
Thank you.
Hello, thank you for your work. And my question is regarding to the training data preparation. You have mentioned that for the source and the target image are from the same video from 2 frames. Yep. And my question is, for these 2 frames, how you prepare the dragging points or the starting point and the target point? Are you using some automatic tools or annotated manually?
Yes, there's so regarding the data set preparation, yeah, actually I should talk more on this, but unfortunately due to time constraint, I can't. For that part, actually we make use of some point tracking algorithm, which in our case will be called tracker 2, V2, and then to try to track like those points that exist in both like source and target frames. So we have also a few rules that try to look for the points with large motion, because we don't want to look for the points with small motion, then it does not learn any meaningful drag. So we also have some filtering rules as well. But in order to look for the trajectories, we are using a existing point tracking algorithm.
Okay. So if there, you have a question.
What I would like to ask is that you have encoded the points before sending it through to get the output. So I'm asking like, how have you encoded it? Is it like a heat map or?
Oh, okay. So you mean the input representation for the point map, right? So in our case, it will be like each point pair will be randomly assigned integer within the range of 1 to 20, randomly assigned. Like maybe this point will be 1, the other point will be 3. But the corresponding points in the source and target frame should be assigned exactly the same ID. Yeah, and then we pass it to a conv network, which is made out of like a few convolution, non-linearities, and some downsampling layers. I believe also try the conv, and then that's all. It's a very simple design.
Okay, understand. So one more thing is also related to the pre-training, not the pre-training, but related to the image processing before you send it to the thing, which is training data preparation.
Oh, okay.
Yeah. So what I would like to ask is like, you have said that you follow some kind of key points to so-called look for the largest movement. What my question is that there may be cases where the video has large movement in many different places. Like in that cases, and there may be like huge cluster of points which denote the same place. So how do you tackle this kind of situations?
Oh, you mean there will be some change in the camera scene, kind of?
Not in terms of camera scene, but for example, if the face is moving,
Uh-huh.
maybe all 20 faces point to the nose.
All 20 faces.
Like the key points.
Uh-huh.
I assume your algorithm works on key points. Key points.
Okay. Actually, we do not really have a sense of key points here. So what we do is that, okay, so the very first stage is to compute the optical flow between these two frames. So we try to sample those with large magnitudes. So those need not be a key point. So maybe I will take a quick look at this figure right here. So as you can see right here, so the points could cover any other places. So it need not really fall on the key points here. So I'm not sure whether that answers your question.
What I was asking is, for example, if all the points falls in one concentrated location.
Oh, you mean all of them actually move into a single place?
Yes. Have you seen these kind of scenarios? I was thinking of how you will actually process it, or how do you tackle it?
Actually, we do not do too much of like filtering on this, and frankly speaking, I did not observe this yet. Yeah, but in general, most of the result looks something like this, which we found to be capable for training. Then we just move on. Yeah, we sample a few and then just take a quick look, and then it seems to be plausible enough for training. Yeah.
Thank you.
If there is no more questions, then let's call it a day. We are already finished all the presentations and we close today's event. I hope you enjoyed today's event and also enjoyed our provided meal, the dinner meal. And thanks a lot for Professor Liu Ziwei and Professor Michael Shou come to visit our office and give us the wonderful talk. And thanks a lot for my wonderful colleagues for doing such amazing research projects and also deliver the good talk. And so thanks for our organizing team for organizing these very inspiring events. That's all for today. Good night.
For the audience, please follow our colleagues here and return the badge, I think. You can keep it.